Um, all right, well, thank you for your patience. So it's my privilege today to introduce Excalibur to you. This is a pipeline that's motivated by population level questions, and it's enabled by uniform processing. And that uniform processing is going to be a theme that you're going to hear going through the description of the Excalibur pipeline. I also want to take the opportunity to acknowledge the numerous and important contributions made by our team, and also the work done on behalf of IPAC to make hosting the Excalibur portal possible. So thank you very much, especially to Dave Ciardi and John Good. And I also want to thank our IPAC folks who are helping make this venue today possible. So thank you very much, Ellen, for working on a Saturday, and thank you, Melanie, out there online. All right, so let's talk about the pipeline. So Excalibur stands for Exoplanet Calibration and Bayesian Unified Retrieval. And it's again, it's the motivation for this uniform processing is that we want to do comparative planetology. So that's the really the driving motivation. And by that, I mean, when we compare the spectra of two planets, we want to know within the Excalibur team and maybe elsewhere, we want to know that the differences in those spectra are due to astrophysics and not due to difference in methodology. And so for that reason, we implement this uniform processing. So to do that, Excalibur is fully algorithmic. When Excalibur runs, there are no humans in the loop. Humans can do two things for Excalibur. You can commit code and you can identify targets. And that's really it. Excalibur is designed to operate on an input catalog. So this is a pipeline that's designed for processing at scale, and it operates on the whole input catalog like operating on a big vector. It is designed to go from the observational data, so the telescope observations of the exoplanet system, all the way through, the extraction, spectral calibration, instrument modeling, estimation of the transit or eclipse spectrum or phase curve, and then do inference of astrophysical parameters using an atmospheric retrieval code. And you'll hear more about that also. One of the big aspects of Excalibur is that when we get a result, we want to know how we got there. And that'll connect to a theme I'll talk about in the high agility architecture. But we want to know how we got there because sometimes things change. Exoplanet system parameters get updated. More data is available. Better methodologies happen. And so we want to know for a given result, what went into making this result. And so for that reason, Excalibur maintains the entire chain of inference. And it does that with persistent data products that are tagged with a unique identifier. And that identifier is associated with a GitHub change set that defines a specific Excalibur processing instance. So for any data product, we have all the we have all the intermediate data products that were used to create it, and we always know what GitHub change set those data products are associated with. And so as changes occur, we're able to map results back into changes in the code base and the data. We also have a number of data product assessment, quality assessments as we go through the pipeline to try to ensure that the products that come out at the end are as good as possible. Excalibur implements a high agility architecture. And the best way to think about that is Excalibur is kind of like Google Earth, at least that's the intent. So Google Earth is supposed to show you whatever the current state of roads and bridges and whatever is when you're driving around. And Excalibur is motivated by the same idea. It is designed to report the current best estimate of exoplanet science parameters given the data and the methodologies. Now, exoplanet science is very dynamic. We're getting new observations all the time. We're getting improved estimates of system parameters, whether it's the properties of the parent star or the ephemerides of the planets that orbit those stars. new methods come along for either data extraction or calibration or instrument modeling. And that is the wonderful and organic progress of this field. And that's due to everybody who's participating in it, including all of you. And so Excalibur is designed to embrace that, but in a way where we can trace the changes to impacts on the results, and that's done through the chain of inference. The high agility architecture is what allows us to take advantage of these changes. And so we have an executive function that is always looking at the code objects and the data objects that are in the pipeline. And when it detects changes, it builds a runtime directed graph, which lays out the processing steps in the pipeline. And here on the right, I'm showing a high level view of one of those runtime directed graphs that shows the flow from the targets down to some of the final stages in the pipeline processing. The Excalibur code is public, and certainly looking at the algorithms and so forth is something that we encourage, but we don't really encourage you to try to install it. Excalibur is kind of like a high performance sports car. It goes really fast, but it spends a lot of time in the shop. Maintenance of the environment that it works in is a pain even for the team. And so I'm flying the red storm pennant if you do any sailing. That installing this yourself is not really recommended. So let's take a little more detailed look at Excalibur as it stands today, keeping in mind that it is a dynamic and evolving pipeline. So here I'm showing a little more detailed view of the directed graph in our algorithmic tree. And to keep you from having to read all these tiny little cryptic names, I'll go through the major functions in blue. So we start with defining targets. So we start with the definition of the catalog. And from there, we go to get data out of the astronomical archives. And we also go and we get the system parameters from the exoplanet archive. Once we have those data, we have to sort them to figure out which of these data are transit, which are phase curves, which are eclipses. We go through spectral extraction and calibration, and then each of these various types of time series have a separate branch in the pipeline. We also have a simulation branch where we're able to simulate catalogs, and we have an ancillary branch where we calculate things like equilibrium temperature, estimate the UV flux that exoplanets experience, and other kind of one and done type of calculations that don't involve retrievals for the systems. For the catalog that we're releasing, it's all transit observations. So it's this highlighted leg of the pipeline. We include all the system parameters because those do have an impact sometimes on the results. And so we have data products for the system parameters, for the sorting, for the calibration, and then the transit leg itself down through the atmospheric retrieval. In lighter blue, I'm highlighting this classifier area. We don't have those products out yet, but this is something one of our team members has been developing this summer, and you'll be hearing more about that from Kate, and hopefully that will be included in the next delivery. So I'll just walk you through at a high level a visualization of some of the data products that are in the current release that are and map them back into this chain of processing. So starting at the top, we have a view of the sorting function. So this is a visualization, and it tells me that there were two transits with observed with two different Hubble visits, and that they had 5 orbits apiece. Continuing counterclockwise, we have a view of the masked spatial scanned Hubble data. Continuing counterclockwise, we have an extracted wavelength calibrated spectrum, and that's for the star. And there's a time series of these, and so they're stacked on top of each other. Especially in cases where there are multiple visits, you'll see the stellar spectra changes a little bit, and you'll see that in the data product. Continuing clockwise, we have an example of a white light curve showing the standard Hubble non-continuous observational series. Below that, we have, I'm showing a transit spectrum with a model fit through it. And it's actually a most probable model from the atmospheric retrieval code. And we also provide the posteriors for that. So this arc of images along the top and right side of the screen are all examples of some of the data products that are in the pipeline. Over here on the left, I have a figure from what's some of the types of data products that are hopefully coming in the future releases. HyESA is going to be telling you in more detail about these data products, and Kate will have a talk on the, sorry, I'm still learning how to drive the pointer. She'll have a talk on the classifier for data product quality, and Gael will be telling you about the atmospheric retrieval code, Cerberus, that we use in Excalibur. So there have been 5 Excalibur papers published to date. 2 of them really used Excalibur in the way it was envisioned. So the first was a paper led by Gael Roudier, which is a statistical assessment of equilibrium and non-equilibrium chemistry in exoplanet atmospheres, and that used the 62 planet catalog that we're releasing. Then there was a second paper that did another population level study that was led by HyESA, and she was studying the impact of aerosols on the amount of spectral modulation supported in these atmospheres. Certainly Excalibur can be used for single target studies. Here's an example of a paper that was I led in 2021. And I'm also showing what since I have an interest in the calibration, I'm also showing an example of a figure from this paper that was led by Noah Huberfili, where he did an assessment of the calibration performance of the Excalibur pipeline across the entire 62 planet catalog. And so that's a really nice type of catalog level analysis of performance that I think is going to be important going forward in comparing different pipelines. If you find the Excalibur data useful to your research, and we certainly hope that you do, we do ask that you just cite one of the relevant papers here. And you know, the first, the top one has a description of the calibration methods. The second one has a lot more details about the Cerberus retrieval code. And again, the third one is this detailed level performance study of the pipeline calibration, and it also has some additional information on the instrument model. So this is kind of a high-level view of what we're releasing. This is the 62 planet catalog, again, that was used by both Gael and HyESA in their respective papers. One of the things I really like about it is it covers the exoplanet, the transiting exoplanet phase space pretty well. So you can see the blue dots corresponding to the catalog planets, and the kind of the gray dots behind them was an estimate a few months ago. So it might have changed a little bit, but the changes are pretty minor. But it's an estimate of the top 1,000 ranked planets for Ariel case survey in terms of the best transiting planets to look at. So the catalog has pretty good sampling, and they're all observed with the Hubble G141 WFC3 instrument mode combination, all using spatial scan, and again processed from the data extraction to the retrieval in a uniform way. I think that completes our introduction, and I will turn the microphone over to the next speaker if there are questions.
Hey, thanks, Mark. You said there were only few knobs for, I mean, no knobs for the users. So I don't do data reduction, but listening to like the JWST folk, there are, down ramps, up ramps. Sometimes they're fit with different parameterizations better. There seems to be a lot of sort of user magic involved in trying to actually reduce the data to get the product. Does Excalibur have a wide range of things, and is it able to identify it for itself what the best techniques are to reduce the data?
So do I need to repeat the question, or is that okay? Really great question. So G141 is the answer is, if you're having to do different methods for different planets, my view is that you should start worrying about doing comparative planetology between those data sets. They've been fundamentally treated differently. That would make me nervous. Excalibur does not work equally well on every target, but it works pretty well most of the time. Actually works very well most of the time. There is a beautiful histogram in the Noah Huber-Feely paper that shows the residual standard deviations as you take a model for your light curve, and this includes the astrophysics and the instrument model, and you subtract that from the data, and then you calculate the residuals. So he does he has a residual standard deviation histogram of the catalog. And the bulk of our planets are right around 2 times photon noise in terms of the residual standard deviations. But there's one outlier. There's one in the catalog that's up at 11 times photon noise. And so, that's an indicator that a planet like that, maybe you want to be careful with. But if you're doing a statistical analysis, the bulk of the catalog, at least by these performance metrics, is really very good. There are planets that people have been able to do tuned custom pipelines for that don't show up in our catalog, right? It's because Hubble was doing something crazy. The guiding was different or something like that. And the Excalibur approach is we throw out a lot of bad data. If you compare the amount of data that makes it through the Excalibur pipeline to some of the other reductions that are out there, we typically end up with less. And that's because we throw out bad data, we throw out bad visits, and we throw out bad sources. So that reduces the overall number that we're able to deal with, but it does mean we're able to deal with them in a uniform way. But it is possible that if there's a really interesting planet and the telescope was doing something squirrely, that will need a special treatment. But again, then you have to wonder, what are the differences that are induced by methodology versus astrophysics?
Yeah, we have one question online. The question is, it looks like Cerebus, or not sure I'm pronouncing that right. It looks like Cerebus is used for retrievals. There was also a reference to Taurex. How is that used?
So the way Excalibur is set up, we can actually swap in more or less any retrieval code we want. We actually have Taurex in the currently running in the code base, but it's not doing any retrievals. So we use Taurex. We were using Taurex for some synthetic modeling. Remember, we have this branch in the pipeline where we can do population or catalog simulations, and we were using Taurex for that. We could, in principle, have 2 retrieval codes, have them both do the retrievals, and serve both outputs. That'd be, the architecture supports that, and that would be straightforward and only limited by computation.
Are there any other questions online? All right, well, okay, yep. Give me my microphone.
I'm not on Slack right now. Should I be?
Okay, all right. They're showing output from Excalibur that shows 8 different visits in the tutorial with each multi-point array points. Is this effectively just from a series of cadence observations? Is each visit its own cadence or a different project? I don't know if that can be answered live or if it's something that should be answered online.
Can I try to take that offline?
Yep, I'll send.
A little unclear. I need to try to understand better what's being asked, but happy to try to answer that. And that goes for any of your other questions. I'll be around at the non-coffee break, and you know, this is a great opportunity to you know, ask us questions, and I really want to encourage you to do that. And I'll be back to talk about more about how to engage the team later in the program. So thank you very much.